And he pointed out that if I hand this directly to Adrian, he's just going to turn around and hand it to the people in this community and say, "Is this any good?" Right? To review it.
That's a good approach.
Right? Yeah. So he said, "Why don't you just run it through? Why don't you just run it through ICNRG, and just position it as this is, just one person's position. There's no, we don't have to reach consensus on anything."
No. Right.
So maybe I should just, propose we adopt it as a, it's just something to run. However,
wait, that's a further question. Do we have to adopt a document before publishing it?
That's a good question for Colin. I don't think so. I would say, I can just produce an update, and you can say, "Hey, let's list Colin."
Yeah, right. I think you just
and point out that this is a checkpoint, and then we're going, as Thomas, I think it was proposed, or maybe Bourdieu proposed, that we just start a new, a new RG level architecture. Thing. And then it can just reference this as prior work.
Yeah, because I think we got into a mode where we were just copying what working groups normally do, but maybe there's actually no need to do that.
Right. Let me fill out the top of the blue sheets. Oh, it's already here.
Okay, good morning. Please find your seats. We're going to start soon.
Yeah, with the 10 o'clock start time, there's no excuse.
Right. So it's 10 o'clock, and then I think it's not that early, so there's no excuse to be late. Okay, good morning. This is Icnrg. Welcome to Singapore. These are my co-chairs, Börje Ullmann and Dave Oran, and I'm Dirk Kutscher. And before we start, so we have an updated Node-well node, so it's important to be aware of that. So first of all, this one hasn't really changed, but so you are still expected to let us know if you introduce IPR or see IPR in the presentations or discussions here. Second, the IETF is also following the IETF's policy, so for privacy and code of conduct. So check out these two RSCs here and talk to the Ombuds team if you have any concerns or questions. And so finally, we'd like to remind you that this is the Internet Research Task Force. So we are doing research here. We are generally not doing standards, although sometimes we use the same methodology. So we do drafts and at some point RFCs. Quite often the goal of the work that we do here is just to enable additional experimentation or enable collaboration on certain topics, but it's really not about producing standards. Check out this IETF primer if you have questions on that. Okay, so Icnrg, as all the other groups, has a mailing list, a web page, data tracker page, and so on. And so for this meeting, Marie-José kindly agreed to take notes. Thank you very, very much. It's not the first time. The materials are uploaded, and this is the agenda for today. So you can see it's pretty packed. So we didn't have a full day interim yesterday because we just had one in Macau. So we're going to talk a bit about that as a summary. I'm not going to read through all of this right now. Just asking around, is there any update, and do you want to bash the agenda? Anything we missed? Okay. So then let's get started. So we had this interim meeting in Macau in September after the ICN conference there. So the conference and also our Icnrg meeting was kindly hosted by the University of Macau. So thanks a lot for that. So we had a kind of interesting agenda. So often we use these post-conference meetings to do a deep dive on certain interesting, for example, paper presentations that occurred at the conference, or some in-depth technical discussion. And so let me just give you a quick summary of what happened there. So Jeff Berkey and team actually organized a full-day workshop before the conference that was called Touching the Future Internet. And that took place at the School of Creative Media at the City University in Hong Kong. And so this was about creating new ways to deal with distributed multimedia and with a specific tool, Touch Designer and NDN. So the background is that say in the old days when we were doing like video real-time streaming and so on, we were mostly concerned with like linear video and these things. Well, actually today there are much richer ways to interact with multimedia. So for example, in these say multimedia presentation environments or theater environments where Jeff works, you are constantly mixing different sources and so on. And so the idea that Jeff and his team had were to provide a good networking support and good APIs for that. And so they actually integrated NDN in a commercial tool. So Touch Designer by a Canadian company called Derivative. And so gave this to designers or researchers in that space. And so for experimentation. And that was a really cool workshop. And Jeff gave us a summary. So check out his slides from the interim if you're interested in that. Cenk did an update on ICN LoWPAN. I'm not going to talk about this now because Thomas is talking about this later. And Cenk also talked about quality of service for ICN in the IoT. So there's a draft in Icnrg about these ideas. And so that team also had papers and demos at the conference. And so in general, the idea is that while QoS, of course, has a long history in the IP world, and in ICN, it's quite interesting to revisit QoS because actually you have much more resources to control, so you can actually achieve better control, maybe more fine granular QoS control. And you also have things like the ICN naming approach, so you can actually also maybe be a bit more expressive about classifying flows and so on. And so especially in the constrained IoT environment, it makes a lot of sense to look at resource control quite carefully. And so this work had a case where they wanted to support really critical IoT communication, so like life-saving alarm signals, for example. And so they looked at, what can you do in an isolated fashion on one node? So how you deal with the different resources, how you can correlate the different, say, ICN forwarder resources on one node, but and how can you also distribute the coordination in a larger network? So with that, I think that should be a good teaser for you to check this out. And then we had a discussion about ICN and low power, long range communication, so LoRa in particular. So you're probably familiar with, say, LoWPAN, the LoWPAN work here in Icnrg, or 6LoWPAN in the IETF and so on. Low power wide area is a bit different, so it's also very constrained, very low power, but wide range, and you connect to something like the internet in the end. So you don't have this gateway model necessarily. And turns out that our different communities in the larger ICN space have been have started looking into LoRa because it's quite interesting. So, for example, we had a presentation from the Hong Kong Applied Science and Technology Research Institute, ASTRI, and they are developing an NDN-based system for smart water meter collection in Hong Kong, and so talked about their prototype implementation and so their ideas on that. And Peter Kitzmann from Riot, from the Riot team, gave us an update about the LoRa support in Riot. So there is a proprietary code by Semtech, so the basically inventors of the LoRaFi protocol, and so that's integrated into Riot. But Riot is also working on a bit more elegant implementation of LoRa into their general networking stack. So basically, LoRa is supported quite well in Riot, and that's good news for people who want to do experiments, also ICN experiments in that space. And so after these kind of more presentation-oriented discussions, we had a in-depth discussion about some design opportunities or design alternatives for doing ICN in LoRa or over LoRa. And so I'm not going to repeat this right now. So we probably continue this, and we'll be able to tell you more about this at the Vancouver meeting. If you're interested in participating, we'll just use the Icnrg mailing list. So please contact me or use the mailing list. Okay, and then finally, Christian Schudin gave us an interesting update about his thoughts about push-based communication, so push-it update 2. So if you have been here before, you remember an earlier presentation where you talked about the general idea and so the motivation for doing like append-only push communication. And so this time he had some more information about, say, some protocol design ideas. I don't think I will do a good service in explaining this because that takes more time, so I just refer you to the presentation. And okay, so that was a quick summary about the Macau interim. And with that, I think we should start with the regular program. Can you bring up the slides? Yeah. If you have any questions on the Macau interim, let us know. Okay. And so the first presentation is will be given by Dave on flow balance ideas. And here's the clicker.
So this is a little low. Sorry, I'm a little tall here. There we go. So those of you who have worked with NDN or CCN-like protocols know that an inherent property of those protocols is that one interest message produces one data message, and you get this property of the overall system called flow balance. So this talk is about some characteristics of flow balance that are desirable versus undesirable, and how we might make some small changes to algorithms and protocols to improve the performance of a flow balance-based flow and congestion control scheme. So this draft has been around for a few months, haven't gotten very much in the way of comments on it, so we thought it might be useful for me to sort of bootstrap the discussion by giving a talk. So the outline is basically, I'm going to give a short background on flow balance and how it's connected to congestion control algorithms, sort of like the baseline bottom line issue, which is whether you're counting interest messages or actually counting bytes as one would do in a classic congestion control algorithm, and end with a protocol proposal for how we might enhance both NDN and CCNX, in order to do a better job of this. Next. So one interest produces one data, which has some very nice properties, including the inability of a node to just inject data into the network, because if there isn't an outstanding interest for a piece of data, any data message that's sent in is allowed to be and likely to be dropped. The second point is that these messages at layer 3, where the ICN protocols run, are bounded by a layer 3 MTU, not a layer 2 MTU. And in the case of NDN, at least in theory, that L3 MTU is essentially unbounded, because the designers decided, for some reason, which I don't want to go into because it will start me on a different rant, that the MTU size is a TLV value, which means you could, at least in theory, have gigabyte MTUs or petabyte MTUs if you want to wait around long enough. In practice, this is limited. There's a compiled in upper bound in the NDN code base, which will wind up being an architectural constant, I suppose, and that's 4K bytes. For CCNX, it's a fixed size field, so the maximum theoretical L3 MTU is 64 kilobytes, same as UDP or TCP in the IP world. So if the problem you're trying to solve is how do you fit this into the L2 MTU, you need fragmentation protocols in the case where the L3 NDN or CCNX message is bigger than an L2 MTU. Next. Oh, how about that? How exciting. I'll probably screw up the clicker, right? Okay. So what's the problem here? The problem is that small data objects, in terms of constructing your ICN level data packet, are inconvenient for a number of applications, because the natural object size you want to deal with is larger than a link MTU. So things like video frames are larger than an MTU. Various other types of, say, row of a database table or any number of data structures are larger than an MTU. On the other hand, you also have applications with very small data objects, such as voice or IP audio data frames, which can be as small as 20 bytes, sensor readings, which conceivably could be even smaller, 2, 3, 4 bytes. And if you don't know how big a L3 data packet coming back at you when you issue an interest is, how do you do the resource allocation in a reasonable way? What people have been doing, if you look at the existing resource allocation algorithms that have been implemented and measured, they make very conservative resource allocation decisions and assume MTU size packets, at least L2 MTU size packets, and in some cases even L3 MTU size packets. And then there's some per packet crypto overhead in terms of how much you have to hash on every packet and what you include in the packet in the absence of manifests, which makes things bigger than you might like to. This is equivalent to the how do I size a data packet when I put it into a VPN tunnel, because I might, the native data might fit on the link, but then I add the extra overhead and I've spilled over and I need fragmentation. So why don't we solve this whole flow balance problem with fragmentation? There's a bunch of different fragmentation schemes. I won't go into what they are. You can do end-to-end. You can do hop by hop. You can do hop by hop with cut through, any of these things. But the bottom line is that this doesn't actually solve the flow balance problem, because you still have to allocate buffer and link bandwidth at each intermediate hop because of the stateful forwarding. And you have to set that aside for the maximum size objects, because if you don't do that, this is similar to the fragmentation problem in IP. You're going to get congestion collapse on overload, because you can't put any single thing back together again in a reasonable way. So here are some design considerations that led to the scheme that I'm proposing here. So you want some means to allocate link bandwidth for data messages with an upper bound larger than the path MTU and a lower bound lower than a single link MTU. You want to at least handle moderate-sized objects. And I sort of took the CCNX view of the world, which is it's unlikely you would ever want to have an L3 MTU greater than 64 kilobytes, as opposed to really big ones. and finding the right trade-off, if you allow really big ones, between handling a large number of small objects or a small number of large objects. If you look at the math, that's very quickly an intractable resource allocation problem. You just have no idea what to do. And in many of these congestion control schemes, resources are allocated for the returning data packet based on the arriving interests, not just waiting around, waiting for the data packet to arrive and doing some kind of tail drop or AQM scheme on the data. So that means it's really useful to know when an interest message arrives, how much data you expect to come back based on the arrival of that interest message. So the solution is actually super simple. You just add a TLV to the interest message saying, this is how big I expect the data coming back for this interest message to be. And you use that to calculate bandwidth allocation for the return hop instead of just counting all interests equally. So that's super simple, only it isn't. So there are a number of problems here. One is, well, how do you know the size? You know, what do you put in the interest message? Well, in a lot of cases, for a lot of applications, this is actually pretty easy, right? For sensor or other Internet of Things applications, the data is instrument readings. These are known by the they're fixed size, they're known in advance by the application protocol, and you can just, you know, tell the L3, you know, this is temperature reading, it's 4 bytes long, right? In video streaming, the information is also available ahead of time in the manifests. These are the application layer manifests, which contain the names of video segments and their sizes, and also for the audio. So you have that information at the application layer as well. And then the case for something like VoIP, almost all the known vocoders have fixed size frames which are negotiated at the start of the session, so you know before any data is exchanged whether you're, you know, if you're doing LP kelp, you know, they're going to be, you know, somewhere between 10 and 20 bytes per sample, right? But that doesn't cover everything. Sometimes you don't know, right? And what if the consumer has to guess? So we need to deal with consumers that guess, and if you allow consumers to guess, you need to deal with both honest consumers and malicious consumers. So the second problem, if you have, if the user is guessing or something that you thought you was right was wrong, the data could be a lot bigger than the estimate. And if that's the case, the data can result in two things. First, you can get unfair bandwidth allocation, where you've allocated resources for this much, but this much comes back. So in the worst case, you can actually amplify congestion by sending back a lot more data than you've allocated the resources for. So you have some number of choices here. I won't spend much time on them. You can forward it anyway, which is safe if you're not congested, but that's unfair and unstable when the link gets congested. You can forward the data when the link's uncongested, but suppress the interest and reject it when the link is congested. Or you could say, well, you know, people misestimating their nefarious characters, so if you ask for too much, you just drop the data as a way of punishing the user for the misestimate. But if you're going to do that, you need some kind of feedback, though, and you'll notice that in the protocol proposal that I'm making, there is an error code that can come back on an interest if you drop the interest or the data coming back due to the misestimate being too big. So the next problem is, well, the inverse problem. The data is too small. So you don't cause any congestion by overestimating the size of the data coming back, but resources get inefficiently allocated because not all the set-aside bandwidth is actually used for the returning data. So there's some things you could do here too. One is to, well, let's just ignore this problem because, you know, if you're doing stochastic resource allocation on the return link, somebody will get to use it anyway. You could account for the usage according to the larger data size that somebody could have said, and then you're sort of penalizing people in the domain of their flow control for that misestimate. Or you could attempt to adjust congestion control parameters around this. It's a little too more detailed for the talk here. Look at the draft for that. And then problem number 4, the one that always rears its head in any of these architectures like NDN and CCN, which is interest aggregation. Because multiple interests can be aggregated at the same point. And what if one of them says the data is 10 kilobytes and the other one says the data is, you know, 64 kilobytes? What do you do? How do you manage this? And again, the draft has a bunch of possible approaches to this. I won't spend much time going through the details here. Just read it in the draft. There's some reasonable approaches to deal with interest aggregation here. By the way, anytime you try to do something clever in either NDN or CCN, you're going to run up against, what am I going to do about interest aggregation? So we see this in the quality of service discussion, which we may have later as well. And then, of course, you have malicious actors. You have people who are intentionally overestimating data size with the goal of preventing other users from using the bandwidth. Or consumers intentionally underestimating data size, and the goal is to sort of have the interest processed while other aggregated interests are not processed. So you can have one user's interests interfere with another user's interests, denying them access to the data. So the simplest approach here, pretty much the one I recommend, is this is effectively an interest flooding attack. Deal with it the way you would deal with any interest flooding attack. There's some more sophisticated things you could do, but there's some additional computational cost in terms of tracking the state necessary to distinguish a malicious from an honest use of the scheme. So from a protocol proposal point of view, this is really simple. There's a proposed encoding. It's a single new TLV. You stick the expected data size in a TLV in the interest message. It goes along with the interest message. Any forwarder can look at it and use it in order to be able to allocate bandwidth for the returning data based on a byte count, which is what most congestion control algorithms would like to do, rather than decimally or stochastically based on a assumed MTU size. And that's the end of my talk. Thank you.
Okay, thank you. Do people have any questions? Going once.
How many people read the draft? Yeah.
Okay.
That's probably, all right. So the goal I have here is to have you find this sufficiently interesting or scary, one way or the other, that you go read the draft and you tell me how stupid the idea is or how wonderful the idea is or what we should do with this going forward. Thanks.
Okay, you can just keep standing there and we continue with Flick.
All right. This is a complete change of topic. So I'm going to talk about an update to a draft that has been around pretty much since Genesis, the creation of NDN and CCN, which is a method for doing manifests, which are ability to describe collections of ICN data objects. So the background is that this has been around for a very long time. The design was done, I don't even remember, probably 2014, sometime like that, around the time of CCNX 1.0. Christian Schuden for CCN Lite came up with an early version of this. That's how it got the acronym name Flick. And in terms of the protocols we're dealing with, manifests are useful in NDN in the sense that you don't have to use them. You could put everything you needed in every single data packet. But they're critical in CCNX because CCNX is heavily biased toward not having all the state that you need to process a data message in each individual data message, but assume that you can get the common pieces of information through an aggregated data structure like a manifest. So the examples here are CCNX is heavily biased toward having what are called nameless objects, which are just the implicit hash of the name together with the data. It's needed in order to take large objects, logical objects, and segment them into data packets of various size. And it's also needed if you want to express collections of objects, the equivalent of like file system directories or database tables. So it's been implemented. It's been around for a long time. It's been in use in real applications for a long time. So where are we? Well, the current state of affairs is that the draft expired in 2018. The original authors have gone on to greener pastures, pretty much, and don't have time to really do much work on it. So I sort of cajoled two of the existing authors to kind of resurrect the work, and we had a meeting in Montreal to sort of say, hey, how do we get this sort of going again? We got a little bit of help from some, but Mark Moscow and I basically said, hey, let's just go get this going. It's a critical piece of technology we need for both of these designs. So after some work, we finally got a new version of the draft published a few weeks ago. So it's alive. How can you say? It's now alive again. So some things haven't changed. Flick still uses this notion of a hash group, which is a group of object hashes that represent individual data packets. That's an ordered list of these content objects that point to either the native data object at the bottom, or you can build a Merkle tree of manifests, so one manifest can point to another manifest in a manifest tree. That's all still the same. It still has metadata in the manifest that tells you how to interpret the manifest using a relatively simple automaton to traverse the manifest. And it also has this nice property, which I think is underappreciated, is that you can encrypt the manifest using different keys from the ones that are used to encrypt the data. And the reason why this is useful is that you may want third parties and intermediaries to actually be able to interpret a manifest to do various types of optimizations without actually giving them the data encryption keys for the underlying data. So what has changed? Quite a bit, actually, since we've learned a lot since in the last year and a half since the work went idle. So the first thing we did is we added this concept of namespaces so that you could really describe how the naming conventions for sub-manifests and data objects work, right? And the prior one just sort of assumed everything was a nameless object. You couldn't have a manifest pointing to a list of entries, each of which had a name, right? So we've defined the three namespaces, a nameless operation, which is to point to hash objects, a single prefix, which says that everything under the name of the manifest is a lower level, next level hierarchical name component, or a segmented prefix where every name is unique. So you can do all three of those things. Obviously, the first is the most efficient since it stores the least amount of data in the manifest. The next one is sort of intermediary, where you're sharing the prefix among the other objects. And the last one is, if neither of those things holds, you can still construct a manifest for a random collection of objects. So each hash group in the manifest can use its own namespace. So the application and manifest namespaces for where you're pointing to things can be different from each other. The second thing that's changed is how can I put this? This sounds really different. It's really not all that different, but there have been some changes to the encryption scheme. I think these are all pretty much for the better. Before, the encryption scheme had some things not covered by the encryption, and hence various pieces of metadata would leak. So we've redone the syntax of the manifest such that no information leaks since it's all encrypted under the key that encrypts the manifest. And it was done in such a way that you didn't have to do data copies. You can do in-place encrypt, decrypt of the data structures in the manifest. We removed one piece of flexibility we had, which is in the original one. You could have different encryption keys in different hash groups of the manifest. We decided that was unnecessary complexity, got rid of it. If anybody is using that, we'd like to know, because we're going to take something away from you. And now there's only one encryption key for an entire manifest or manifest tree. We specified in detail how you do pre-shared key encryption and group key encryption for the manifests. Group key encryption is probably the most useful for a data structure like this. In terms of processing the keys and the actual encrypt-decrypt, it turns out that they devolve to the same underlying code that you'd need to make it work. And we added extensibility mechanisms, so both the encryption mechanism and the key location mechanism for getting the keys to decrypt the manifest are extensible. So we can add new key location capabilities, we can add new encryption schemes. Second thing that's changed is we've enhanced the metadata. So the manifest metadata is sort of completely refactored. It's in different places physically in the data structure than it was before, allowing both direct and indirect subtree hashes. And now the way manifest metadata is handled is exactly the same between the node level, which is for the whole manifest, and the hash group level, which is for subsets of that. We added a general extensibility mechanism, so if there's any manifest level metadata you'd like to add to something, hints about video coding, if it's for video objects, hints about time series semantics of sensor data ratings, something that's application specific, you can put stuff in the manifest rather than having to go out and actually fetch data objects for the application in order to discover those sorts of things. We also added metadata on the pointers in the hash groups. So now you can have annotated pointers as well as plain pointers. And the annotated pointers allow metadata and extensions on every pointer. So a good example here, which reflects back on my previous talk, is that you can put size information on every pointer so that just by parsing the manifest, you know what to put in, for example, one of these expected data size things when you go to fetch something. You can also use this nicely if it's a linear data object, like a large file. You can use this for seeking, because once you have the manifest, you know the length of everything and you know where to go to get a particular byte in a linear data structure. You can also do hints for traversal order. If you have a video application where you would like to fetch things in an order different from the order in which the encoder produced them, decoding hints and all sorts of other things. So the only thing we've added to the actual spec is the size extension for annotated pointers, but it's extensible. You just register TLVs. So number of miscellaneous changes, locators, which are names that are topologically sensitive, where you can have multiple names for the same underlying data based on a manifest. These can now be an array as opposed to just a single locator. So if, for example, you have a set of data that you want to name with a manifest, then you want the names to allow you to stick producers in the infrastructure of multiple service providers, such that the actual names are rooted topologically with the service provider, but still maintain all the security and keying of the application. You can do that. There's a lot more detail in the draft. It's expanded probably to twice the previous size. There's a lot more explanatory material. And we now have a Python implementation, which is not exactly the whole draft, but pretty close. So we've added to the implementation enough for you to start working with it. There's still a few things to be done. We're not quite ready to last call this. We intend to do some more work between now and the end of the year to update the two implementations and get the Python implementation up to date. We're missing an IANA consideration section, which is just mechanical stuff that we need to register things. And we don't really have a security consideration section, which is, in fact, a big problem, and that sort of like needs to get written. So we're done. Thank you.
Cool, thank you.
Questions? Questions?
So
you should look at this. It's really important if
Yes.
you actually want to build applications for these things.
Right. So yes, as Dave mentioned, this is really a critical piece of work, and so we'd like to publish it as one of our specifications next year.
If you thought this was a good thing we did, send a thank you note to Mark Moscow, because this is not his day job.
Yeah. Right. So we, as chairs, we really like to encourage people reading this draft. And so if you are working on any ICN implementation, please look at it very carefully. It would be great if you could even consider implementing it. So again, it's a key piece of technology. It can do much more than just enabling the use of collections. Could also be a tool of supporting a better cooperation between nodes and the networks, as Dave pointed out. So it's would be good to have more people looking at this. Okay, thank you. So next is Jongha giving us an update about the name resolution work. The second from the left tab is the right. No, maybe third.
BBC the data.
Please stop your video streaming right now. We need the bandwidth for slides. Sorry about that. There's still some progress, I think. So,
Sometimes hitting refresh helps.
yeah. I had this before, not this morning, so it's, I don't know.
Or not. It's interesting. It says it's done and it hasn't shown up. Uh-oh.
Okay. It maybe reload one more time. I don't know.
Oh, you're going to try and do it from yours?
That's maybe the best way.
Just stick.
No, will the clicker work? You may have to move the clicker to your machine as well.
But the network is fine. It must be the laptop.
Okay, great.
Okay. This is for update on NRS document. I'm Jung Aung from F3. We have two documents on NRS. One is the design guidelines for NRS in ICN, and the other is the architectural considerations of ICN using NRS. And the first one has been, the title of the first one has been changed from the requirement to the design guideline. We have discussed according to the requirements for a long time, but last meeting in Montreal, we have updated and changed the title to the design guidelines. And we asked for the RG last call for both documents in Montreal, and we got some comments through in the mailing list, and I just copied the David's comment for the two documents. And the first one, for design guidelines, the technical comments may require a second last call, but the other architectural consideration documents, there are some technical and editorial comments, but those can be resolved without requiring a second call. And these are a scope for both documents. The first one, design guidelines, focuses on the NRS itself as a service or as a system in ICN. And it provides the NRS overview and NRS functionalities and NRS design guidelines as well, and security considerations. And the other one, architectural considerations, focus on things related to the ICN architecture. So it describes how ICN architecture may change and what implications are introduced within the ICN routing system when NRS is integrated into ICN. So when you look for the NRS itself, you have to see the first draft. But when the second one is related to ICN, but is focused on the ICN architecture, not the NRS itself. So these are the difference of the two documents, and we added we added in the introduction a cross explanation of the two documents, which was the comments from Dave. And for the design guideline document, we try to address all the comments from Davis, and I'm very sorry that I haven't sent out how we address the comments by the mailing list, but I explain it a little bit for now, and then I try to send that out as soon as possible during this IETF meeting. So please look, please have an intention on the mailing list and give us a good comments as well. And we mostly accepted and agree with David's comment, but the content discovery terminology, Dave suggested change it to the information request or content request, but we changed it to the content request routing. The reason that actually the part that content discovery written was we explained how ICN routing step work. Actually, it was quoted from the ICN Research Challenge RFCs. In there, what ICN routing step is, one is the name, the first is the name resolution, and second is the discovery, and third is the delivery. But instead we just copied those terms, we put the contents in front of the discovery and the delivery. But I think it made some confusion on using the terminology of the discovery. So our intention was the content request the routing. So we changed it, and there are some few parts that we use the content discovery originally. We tried to change it all, but we missed the two parts, so we'll fix them in the next revision. And similar comment from the Mark. What his comment was, it would be good to clarify discovery term in this document. But and he also mentioned there are two discovery, which is one is name discovery and the other is content discovery. But we consider both because in this document, we try to consider any type of NRS to show the possible functionality of the NRS. But the discovery part is not the main issue of this document as well, so we deleted the term. And also this discovery terminology has not been defined even in the terminology document. So I wonder if it is too late to edit the discovery term in the terminology or not, but we can consider about it. And the third person's comment, it would be worthwhile to include some reference to ongoing 3GPP work. So we stated as some short sentence to reference 3GPP work, but I'm not sure if I added the right reference what he asked for, but I will check for it later. And there was a various comments, and we mostly reflected, and I answered and send out how we addressed it. I sent out by email this morning. And there was a Poyan's comment. He gave us a lot of comments, which was good, but that was a good discussion for ICM, but it was a little bit out of scope of this document. So we accepted some of his point, but we denied some. But also I sent how we addressed and what was the out of the scope in the mailing list as soon as possible. And the architecture considerations documents, there was only David's comments, and we reflected, but we couldn't quite complete all his comment for this revision. So what we're trying to do is we'll complete it as soon as possible and submit it soon again. And for now, I only mentioned about one of his comments on NRS caches. So we assumed the NRS reserver have cache. It was because NRS cache could be helpful for such a case of the live streaming services, for like a time critical service. You don't have to do the NRS reserve every time. So for that case, we assume the NRS caches, but because of that, there is architecture considerations for cache. Yes, when you use the cache, there is always issues on cache, but which is not directly related to the NRS issues. So we haven't addressed much for this revision, but we'll fix some part in the next revision. But since the caching, I'm not sure is related to the ICN architecture or the NRS system. So we'll look for which draft could be the better if we mention about the NRS caches in the draft. Yeah. Thank you.
Okay, thank you. Any questions?
Thomas Schmidt, HW Hamburg. I have a question regarding Puyan's comments. If I remember correctly, Puyan was mentioning the problem of name administration and enforcement of the name distributed name administration. Did you address this?
Names, not really, because the namespace we mentioned in the draft, but in this draft we are not trying to show or discuss about the namespace itself.
Well, the point, I mean, if you just look at the DNS, I mean, the way the DNS is built, it enforces the distributed administration of names. So I can't just change the name of Google or something. And that is actually an important point here. That's why he rose it.
Yeah, well, Puyan's comments was mostly related to was related to the DNS, and I think the NRS is similar to the DNS, but is different. And maybe I can make a reply through the email. Then you give me more comment.
Hi, Stu Card. My question has to do with the earlier draft, the design guidelines. In security considerations, 6.1 accessibility, second paragraph, the NRS may support access control for certain name records so that only users and producers within the proper lists can access these records. So that assumes the traditional access control list model of access control. And I think name resolution naturally maps better to the capability-based model of access control, since essentially these are pointers, references, et cetera. I wondered if you wanted to address, capability-based access control in addition to ACLs.
Oh, okay, thanks.
Do you want to respond to that, or?
I think he give me a comment. Was he asking or?
You can.
Well, we'll consider your comments. Okay, thank you.
Okay, good comments. Thank you. So this is basically still in last call, or I think the one draft may be updated, right?
Yeah.
Yeah. Okay. Okay. Thank you, Changha.
Thank you.
And so next is a new speaker. It's called Dave Oran. Talking about path steering. He's called.
Feel like I'm getting unfair bandwidth allocation here. While we're getting the slides up, let me preface the talk to say that this is work based on a paper that Yuri Moshenko and I published in ICN 17 that turns out perhaps has more than just research, more than just a little bit of interest in the community. So we decided that maybe rather than just sort of go read the paper, we would take it a step forward and explain a bit about how we might want to do this as part of the CCNX and NDN protocol architectures, and so people could actually use this to move forward on application development rather than just seeing some research results. So think of this as a proposal to enhance the protocols using the work. There's for those of you who have read the ICN paper, you can go to sleep because there's practically nothing here that isn't in the paper. The biggest job was converting LaTeX to XML, but we all know that. How are we doing here? Not so good. Oh dear. What happened?
I don't think it's getting the signal.
Was it working when it was on Baudier's laptop? Let's switch back. Yeah. I'll try to do this quickly because I want fair time for other people at the meeting. There we go. Just put it in full screen. All right. Oh, you have to move the clicker. Great. All right. So quick outline. I'll give you a bit of introduction to the background of path steering. Talk about the design of this path steering scheme, a bit about the packet encoding, and when you do things like this, you may have some additional security considerations over pure longest name prefix match style forwarding. So here's the problem statement. As we know, the communications capabilities of these ICN protocols are both inherently multipath and multi-destination, which says that if you launch an interest, the forwarders have the capability of spraying those interests over multiple paths and reaching multiple destinations that match the name of the object of data that you want to return. However, we have no mechanism for consumers to affect the selection of which path among the feasible paths gets used for any given interest data exchange. So the forwarders can spray the packets on the various paths, and when failures occur, it's kind of hard for the consumers to actually figure out what's going on. They may be getting performance glitches because if the packet goes over one path, it hits a failure of some sort. If it happens to be selected for another path, it doesn't. You have a very difficult time figuring out why your performance is what your performance is. So some of the motivations for employing the ability for consumers to steer packets on the path is to monitor and troubleshoot all these multipath network connectivity problems, right? Which don't exist so much in IP because IP basically only supports ECMP and not general multipath, and also doesn't support multi-destination since the addresses expressed are either unicast or anycast addresses, and multicast and IP is a whole different kettle of fish. So you'd like to be able to do that and have tools like the equivalent of ping and traceroute in IP in order to diagnose problems. Secondly, in order to measure the performance of a path, you need to be able to send multiple probe packets down that path to figure out what the properties of that path are from a performance standpoint. And if you can't control whether a given interest message gets allocated onto a particular path, you have no way to do any kind of fine-grained performance measurement of your paths. My particular interest in getting into this work was because of the work I did over a few years on multipath congestion control, because some of the more sophisticated multipath congestion control algorithms actually require you as a consumer to count the number of available paths, uniquely identify those paths, and allocate traffic according to the capacity of those paths proportionally. So there's a number, if you look in the draft, you'll see a bunch of references for a variety of multipath congestion control schemes that depend on the ability to steer packets on the paths. And then there's interesting traffic engineering and SDN possibilities here if paths can be preloaded for traffic engineering purposes into forwarders via third party that has done measurements or other types of exploration. So here's the design. The first question you have to ask is, how do you label the paths? And from our point of view, the mental model you might want to have, which is a little dangerous, is something like source routes or MPLS LSPs or segment routing enumerations. It's not exactly the same, so be cautious. But at a high level, we're basically constructing a data structure that contains information about every hop on a particular path. So in the paper we published, we examined a number of possible ways to encode this information, including Bloom filters and this very clever thing called Cantor pairing functions, which go back to your CS days and look at them. They're very cool. They wound up only working for short paths for us, but very cool data structure. A label stack similar to MPLS, but we chose instead to use fixed size labels and a polynomial style encoding for what we propose to put in the protocol. It seems to have the best trade-offs in terms of flexibility, size, and processing overhead. So the way it works is pretty straightforward. An interest contains a path level marked as something called discovery mode and is forwarded normally through the longest name prefix match in the fib. When a content message, a data message comes back, it carries the path label, which has been modified on every hop to add information. And what is the information that's added? The information is a next hop label for every next hop that a future interest would do. So then once you get back this data structure in the path label in the data message, you can insert that into a future interest message, and that interest message will be routed over the path that was previously discovered. So you do a longest prefix match. Within that fib entry, there'll be this matching of the next hop code point, and that will cause the selection of the outbound face under that fib entry to be selected for that data packet, for that subsequent interest packet. So it's relatively straightforward. Some obvious advantage of this, an ICN ping application can reliably measure the path RTT by sending multiple interests over the same path, and then you can measure the path. A trace route application can iteratively discover multiple network paths. Now, one thing I'll bring up really briefly here is there's partial overlap here with the existing work in Icnrg on CCN info, which has a separate forwarding strategy for doing path exploration and discovering all the possible paths that the various fibs contain, returning those, and then being able to diagnose. That's clearly more powerful. It's potentially higher overhead, has some other different characteristics. So we're not necessarily proposing that this is an alternative to CCN info. It's another tool in the bag of tricks, okay? So the consumer multipath congestion control algorithms can discover and distribute load across the paths. And as a sort of side benefit, if you suspect you're getting a content poisoning attack because of the way the particular path that was selected by the forwarders passes through a poisoned cache, you can select a different path which routes around potentially poisoned caches. And then a brief mention, you can do traffic engineering solutions if you happen to believe the SDN religion for pushing everything into routers via third parties. So what are the complications here? Well, the clear complication is how do you invalidate paths if the routes are changing, right? So with path steering, you still use the prefix match to find the set of next hops for which the path next hop is chosen. So the only time you need to invalidate a path is when you go look up the next hop in the fib entry for that forwarder, and the next hop label that you had there is no longer there, right? So if next hop selection fails, we have a way of returning an error that says oops, invalid path label, return that to the consumer. He can invalidate that path, potentially just try other paths or discover other paths. There's an option. You can either reject it or silently forward in case the user doesn't really care. And you can control this behavior through some options that we provide in the path label data structure. So the next hop labels are assigned every time a fib entry changes. And on the reverse path, the data or the NAC is dropped if you're returning returning data for a path that is no longer valid. Okay? And the forward path, the interest is NAC'd. So the packet encoding is a very careful trade-off between how big this has to be to handle longish paths, more than a few hops, and how much compute you need to do to actually select a particular path in terms of computational overhead. So we add a new hop-by-hop header, which is the path label, and the individual next hops is constructed as a bitmap, and that are actually 12-bit chunks. Here's a quick picture of the data structure, which contains the path label, some flags, which is like discovery mode and strict versus fallback mode, and something called the path label hop count. And this is an important thing. It does two things. One is it tells each forwarder where in the path label bitmap to extract the particular next hop label you want. The other nice property it has is, since this will count opposite the hop limit, you can detect when you have traversed forwarders that don't support the path labeling. Need me to finish up. Okay, I'm almost done. So we use 12-bit things, which is a trade-off between how quickly you need to invalidate paths in order to not have aliasing, and how much space you need to do. So some security implications real quick. Clearly, consumers can try to maliciously missteer interests, because if you use a 12-bit next hop label, you only need 2 to the 12th interests in order to explore and find a valid next hop label to try to exploit. So to mitigate this, you just periodically update the next hop labels to maximize the lifetime of paths. And the path label can also be encrypted hop by hop. We have a hop by hop encryption capability that doesn't require any key sharing, so that you don't leak topological information to consumers about all the forwarders on the path. There's some cache pollution potentials where a consumer and a producer can collude to cause poisoned information to be returned over certain paths. So there's a relatively simple mitigation here, which is you annotate any cache entry with the path that the data came over, and if it's different, you don't evict good entries with maliciously constructed entries. And I'm done. Thank you.
Great, thank you. Any question?
Obviously, I'd like to see comments on the list about this. I think we might want to progress this forward as a RG item.
Right, and check out the ICN conference paper that Dave mentioned. Okay, next is Thomas Schmidt. Also a new draft on time TLV. And we are bringing up the slides.
Oops, thanks. Here we go. So this, oops.
Yes,
Okay. Hello, everybody. This is a new draft, but actually this is not a new subject. This is inspired from a discussion we had in earlier meetings here. And this, it basically ranks around the other draft I'll talk about today is this ICN LOPAN. If you remember, of those who have been here, remember, we have been involved or have been working on compressing data that is to be transmitted in IoT constrained environments. And the reasons for this is that there's low bandwidth with high latency, slow links and energy constraints. So we actually want to save as much bandwidth and as many bits as possible, similar to what the people in the IP world do. And along this line, we came across the timers in CCN and NDN. And these timer values are relatively large numbers. They're usually NTP timestamps, and we were thinking about how to compress them. Just looking at the data structures, we have in the interest, we have two timers. One is the signature time of the interest message in the case an interest is signed, and we have the interest lifetime message, which is a relative timer. And that describes how long an interest should be maintained in the PID. At the data sides, we have even three timers. One is again the signature time, the time when the data was signed. We have two other absolute timers: the expiration timer and the recommended cache time. Those are also absolute timers, whereas the interest lifetime is a relative timer. And the idea is to do better on compressing these timers. We had the proposal in the ICN low-pen draft, but the problem is if we compress times, as I will just discuss here, then we can't recover in all cases the original times. And now the idea was, okay, why don't we try to adapt the spec of CCNX so that we actually choose timer values that can be compressed and recovered completely. Yeah. So, brief look at the current representation of timers. We have the relative times and the absolute times. The relative times are time deltas in milliseconds, and they can be 1 to several octets, so they are flexible. The absolute times are inflexible in the sense that they are NTP timestamps and have 8 octets in length. So that's actually a pretty large number. Oops. The idea discussed already along in the ICN low-pen draft, and which is actually harvested from the IP MANET world from RFC 5497, is to represent times in a logarithmic scale, so that you actually can express in 1 to 2 octets a relatively large range of times, but with different granularity. For small values, you have a fine granularity. For larger values, you have a larger coarse-grained granularity. The idea to integrate this in CCNX is very simple. If you have a delta timer with a TLV length of 1 or 2 bytes, then we assume that this is a compressed timer. Otherwise, it is just a normal representation of CCNX. So, just to give you some numbers or some ways how to do this in a 1 octet case. So, what you do is you take your 8 bits and you fix a certain amount of bits as the exponent and the rest as a mantissa, and then you build timer values. Where is this? Is this? No, you build timer values as how you see the equation there, constructed as the mantissa times the exponent 2 to the b times the value c. That actually fixes the range. So we have to fix 3 values: the length of the exponent, the length of the mantissa, and this c value. Here are the examples for length a equal to 3, b to 5, and c 1001 over 1024. And those are actually the numbers taken from the RFC previous mentioned. That means you have a range of expressiveness between the smallest value is the C and the largest is about 45 days. We can, of course, use other timers, other ranges for other expressiveness. So looking at the timers again, we have the absolute times, and the absolute times are difficult to compress such as delta times. Looking at the signature timers, these signatures can be in the past, so you can't express them as deltas. They can be far in the past. They can have they can have basically all values. So we are not addressing to replace those. But we're looking at other absolute timers here, and this is in the data. There's the recommended cache time and the expiration time. Those are also encoded as absolute values in the CCNX spec, but could be actually changed to like taking the signature time as the baseline and then using deltas to express the expiration time and the recommended cache times. And that will be a discussion we would like to have with you or have on the list, whether this should be done or shouldn't. That would actually change two other timer values into much shorter encodings. Yeah, what will be the next steps? Well, we would probably investigate a little bit about the ranges that are appropriate for the different applications in the different delta timers. For instance, for the values I showed you would be very nice for interest lifetime, I believe, but they may not be appropriate for the delta times in the object lifetime. Yeah, and otherwise, I guess the question is whether this is the research group will be interested in just doing this work or changing this spec, because it's actually a very small thing to do. But I mean, a decision on whether we want to change the timers in CCNX specs. Thank you.
Thank you, Thomas. Right, so that was the important information at the end. So the whole idea of this work is well, to unify the time compression that has been done in the, say, IoT space before, and say possibly update the CCNX specs with that. And so that's why I think it's important to for people to review this and basically tell us what you think about it.
One thing I forgot to mention, I mean, some of these timers are part of the signature of the envelope that is signed. So if we cannot recover this, the timers under the compression, we cannot actually compress these timers without destroying the signature. And
right.
That's one of the major motivations, actually.
Yeah.
Sorry, I forgot this. Okay, the other is just a very brief recap, or just a very brief addition to what happened to this ICN low-pen draft. This is actually has been presented several times, many times here, discussed in quite detail, has matured and is about ready to go. So what did we do? We had several reviews also on the mailing list, in particular by Mr. Shi. Sorry. I have trouble in pronouncing. So he had also he commented on several things. The last were on typos and on hop ranges. What we also did is we harmonized the ICN low-pen draft with the time TRV draft I just presented a second ago, so that those fit together nicely. And the second discussion question we had from the Montreal meeting was this draft originally concentrated on efficiently compressing like the default standard cases, and as a default standard case we identified the generic name components for named object, for the names of object, and this is actually what is shown here. So what we do is we have a we compress the names under the assumption that the names only consist of generic name components, limit the length of the name components, and then actually we compress it down to a very short name. There has been the discussion on the mailing list and also in Montreal whether we should include types. Types here should also account for type name components. And Sheng made a proposal in Macau to just have fix a certain kind of types, like version numbers and timestamps in these names to make this more expressive, to include some types, which led to another discussion on the mailing list about, there are other types that are also interested. And actually our way out of this discussion, because we can't really judge on what name types are the most interesting and what are not, is to make this an extensible thing. So the idea is we have in the ICN LOPAN, we have, you want to interrupt or?
No, keep going.
In the ICN LOPAN, we have dispatch fields, and these dispatch fields can be extended. They have extension fields, and the idea is to define such an extension field here that has two further values to incorporate flexibly name components, for instance, defined in dictionaries or in something else that could be actually specified in future documents, which are not part of the spec. You want? No?
Are you done?
Well, basically, oops.
Well, actually, it's appropriate to that slide. So
Sorry?
I'll ask it now, or just make the comment now. Go back one.
Well, this is basically I wonder, is this
So,
wrong?
This seems to me, anyway, to be a poster child example of something that you could use manifest metadata for.
To explain what dictionary you're using or so, yeah.
That's right. So for a whole given, subtree of objects that use certain name type components, you can put in the manifest metadata. These are the ones that would be compressed.
That's actually the extension, what I wanted to show anyway. But the point is, in these extension headers, you would encode a compression strategy. But
those have to be in every packet. That's
Sorry?
why I said those would have to be in every packet.
That will be
So just think about using manifest metadata. It seems like a nice trade-off.
Okay, so we think about the manifest metadata, and otherwise we think we are pretty much done with this draft. So we are asking for the last call.
Right. Thank you, Thomas. So just on the last point, we have to find a way to deal with these dependencies in a meaningful way. So if you think about the manifest approach, I hope this wouldn't affect this current draft. So we don't have to wait with this draft to figure out a way to use manifest for the dictionary description, right?
Yeah, I guess we think about this manifest and take it to the list. The price we are discussing here is actually relatively low. So, defining additional dictionaries would mean that we have one octet, extension octet here, which is also not that bad.
Right. So I think from our perspective, it's a good time to last call this draft now, and it shouldn't keep us from thinking about the manifest idea later. Yeah. Okay, so we will issue a last call on the main list. Please have a second look at the draft. This is also going to be an important specification for ICN in IoT. So. We want to publish this because it's important for building IoT solutions with ICN. Okay, so next is Greg. I saw him coming in with an update on IPOC, which we recently adopted as a research group document. And who stole the clicker? Oh. Thank you.
All right, thank you. This will be a fairly short update. So I'm giving this update on behalf of my co-authors, Smith and Cheng Yu. So the concept, if you're new to IPOC, it's idea to use CCN as the forwarding plane for a mobile core network. So not running CCN on top of IP, on top of LTE, EPC, and things like that. Essentially use CCN as that forwarding plane, and then run existing IP services on top of that. And so IPOC is IP over CCN, and the idea is that it would replace LTE, EPC, and the GTP tunnels that are used for that for mobility. And then once you've got that forwarding plane of CCN in your mobile network, then you can now deploy native CCN applications and get all the benefits that in-network caching and mobility that comes along with that. Status. So I did a fairly detailed presentation on the protocol at the interim before the Montreal Icnrg or IETF meeting. Link is there if you want to take a look at the slides from that. So I'm not going to go through a detailed overview again today. After that meeting, there was an adoption call on the mailing list, and it was adopted. And shortly thereafter, well, a couple weeks thereafter, I updated the draft and submitted that as a research group draft. Changes were pretty minor. Added one reference in response to a question on the mailing list, and then I updated the references to the CCN documents since they had become RFC around that time. And that was it. Open items, there's only one open item that I'm aware of, maybe unless I'm forgetting something. And that was a comment from Thomas about consider including a comparative discussion of mobile IPv6 and multicast mobility. We've had some offline exchange via email and plan to sync up sometime this week to discuss that.
Yeah, I just can add, I mean, the point is you're trading CCN mobility versus IP mobility, and you're in a research group. So it makes sense actually to position between the two. And I mean, multicast is interesting in this case because CCN is also a reverse path forwarding. So multicast mobility is actually the direct counterpart of your approach. That's at least for scientific completeness, I guess.
Okay. Yeah, I have no objection to doing that. I think that we could come up with a short subsection in the document that discusses that. I wouldn't want that to become, the bulk of the document, but we can certainly cover that. And with your help, Thomas, since I'm not an expert on multicast mobility or actually on mobile IPv6 either, appreciate the offer to help. So that's it. I think unless there are further items that come up on the mailing list, either as a result of this, I'd suggest that once we've gotten some text together on that the research group could consider a last call.
Okay, thank you, Greg. So just one question from the chairs. So you keep using the term CCN in this document. Shouldn't it be CCNX? Or?
It should be. It should be. Thank you. So, a second open item, I guess.
Okay.
Any other questions? Thanks.
And that's one question.
So I just want to confirm about the deployment strategy in ICN in 5GC. This is not relevant, but I want to confirm this is like the first model or second model is overlay or underlay, because we are quite confused about that definition. So is this part of that study in the deployment consideration or not? Or which one?
So IPOC is discussed in the CCN over 5G draft. And I'm not remembering exactly the terminology that was used there, but essentially it is using CCN forwarding natively over Ethernet or over another layer 2 technology in the core network and not with IP underneath it. And then running native CCN applications or IP applications, in particular, in this case, IP applications on top of CCN as that forwarding plane. Is that answer the question.
And your name, please?
Okay. By the way, the mic is not picking up the voices really well, so you have to move really close to the mic if you say something. Okay, so it sounds like there's going to be one more revision, and then we might consider last calling it, right?
That's right. I think we can probably get these edits done in the next, well, by the end of the year, so next few weeks.
Okay, sounds very good. Thank you, Greg. Okay, so moving on. Next is Dirk Trossen. Is he in the room?
No, it's not Dirk.
Oh, sorry, yeah. Also a new draft on internet services over ICN in 5G LAN environments. If you can just put it up.
Hello, everyone. This is actually it's a version 0.0, but actually it's a revised and renamed draft we presented in last meeting in Montreal. It's about the so we replace the old one, the IP over ISN over 5G LAN. So right now, the ID I'm presenting now is we call the internet services over ISN over 5G LAN. In terms of ISN over 5G, actually we have another related work on RG draft enabling ISN over 3GPP's 5G next generation core network. So in that draft, talking about how to extend the 5G control plan and data plan in order to support ISN over 5G network or 5G system. So the current one is kind of take that step a little bit further. Is think about if we have the HTTP, for example, internet services such as HTTP, if you want to run it over the ISN, and also here we focus on 5G LAN because 5G LAN is kind of virtual LAN group of some UEs. So we want to look at this, how to support this, utilize the ISN as an underlay, and also utilize the ISN as a kind of a slice in 5G LAN environment in order to support the upper layer, the upper layer internet services such as HTTP. So basically, in this draft, we presented two use cases. One is about the control plan, because control plans, the 5G control plan, they use HTTP protocol is kind of internet services. The second use case we include in the draft is called the HTTP streaming. So we introduced a 5G LAN architecture according to the specification, and of course it's ongoing still in 3GPP. The architecture for 5G next generation core network in order to support 5G LAN. More covered content in this draft is the mechanism and also the architecture in order to support the internet services over ISN over 5G LAN. For example, we need to introduce the ISN API in order to support upper layers. For example, through this ISN API, the upper layer, such as HTTP, they can call this API to send the packet, the data, to the ISN layer. As a part of that, we also consider the service proxy operations in order to support the legacy devices, which means they don't support the ISN natively. So for those kind of legacy devices, they talk to the service proxy operations. From there, the service proxy they can translate the legacy device operations to the, we propose the ISN over 5G LAN. And also part of that is we need to have a component we call the name resolver in order to, discover and find the path ID, because even though we use the ISN as the underlay, we still use the path-based forwarding For example, in order to send one ISN packet from one UPF to another UPF. Also, we also consider the dual stack device support, because in some cases the device support conventional IP protocol also support we propose here the inter-services or ISN over 5G LAN. And then the deployment considerations, we basically took the guidelines from the research group document about the ISN deployment guidelines. Specifically, two guidelines we were taking is ISN as an underlay, and also since we are here considering how to do that over the 5G LAN, so we also take the ISN as a slice, because as you know, the 5G system supports network slice nicely. That's kind of main content, including this draft. So we received a few comments back in July in Montreal meeting. So we made some those two major changes. Number one is add a paragraph to describe the how to realize how to achieve this inter-services over ISN over 5G LAN under some other transport networks. We talk about the SDN transport networks in section 4.1. Here, the 4.2, we added a paragraph to clarify. We also can use the beer traffic engineering as one type of other transport networks in order to support the inter-services over ISN over 5G LAN. So essential idea was to basically say the beer traffic engineer controller is quite similar to the SDN controller. So we can basically do the similar thing, configure some, the bit positions and the bit strings in order to utilize the path-based forwarding, again, for example, from one UPF to another UPF. Another change is we replace the IP services with the internet services. One of the reasons, also commented by the folks last meeting in Montreal is, I think the inter-services is more meaningful and more consistent with the content, with the motivation covered by this draft. That's kind of two major changes that we made so far. Of course, there are some other future updates we plan to do. For example, currently we have two components: the flow management and also the mobility handling. So those two components currently is TBD. We plan to under the future updates. For example, for the flow management, we plan to describe how internet transactions are mapped onto a single transaction relation with the joint flow control across all transactions. I'm not going to repeat this, the preliminary thinking, but the plan was to add, more description and more content around those two components: flow management and mobility handling. Another thing we plan to do is we plan to show a demo in next meeting 1.7 in Vancouver. The plan was to showcase a realization of inter-services over a layer 2, for example, the SDN transport network, using the ISN-based routing. Of course, we mentioned one of the components we propose is service proxy. So the terminals, both terminals, as well as the service proxy-based solution, will be demonstrated, and the use case, of course, will be in line with use case described in this draft. For example, the HTTP video streaming or video viewing. Yeah. Dave, you have any feedback or question?
I'll wait. Just keep going.
Yeah. I guess I'm almost done. I guess. Yeah.
All right. So, quick question. You're running HTTP on top of an ICN protocol.
Yes.
So what spec defines that mapping?
So you say what spec or?
Yeah, what specification defines the mapping of HTTP onto the ICN? Because I didn't see it in this draft. This draft just sort of hand waves and say we map HTTP on top of ICN.
I guess one of the idea was to the ISN, because HTTP and ISN, so basically you're asking how to map, right? Because both layers or protocols are quite different. One of the idea is we're going to, the ISN is going to be extended by providing certain API to the upper layers. For example, four APIs were described in the draft is send the packet and the collection. So using this, let's assume this ISN API is there. So in order to use HTTP, send a packet from the source to a destination, the sender, the HTTP layer and the sender is going to call the API and call this ISN API, talk to the ISN layer and the sender side, and then send the packet down to ISN layer. From there, the ISN layer is going to, use the ISN mechanism plus the path-based forwarding in order to send this ISN packet. Of course, the payload will be the HTTP packet. Send this ISN packet, for example, from one UPF to another UPF, and eventually the destination UPF is going to, recover the original HTTP packet and eventually send it to the UE, for example. So basically, to answer your question, if I understood correctly, there will be something we need to propose and we need to extend the ISN layer. For example, here is by providing certain APIs to the upper layer, like HTTP.
Okay, thanks. Just quick thing that still has me confused, but not to take time here on it, which is that sounds like that requires at least double the packets of a native HTTP.
So why don't we, dive deeper into this when you do the demo in Vancouver? That would be nice if you could explain how the HTTP mapping really looks like.
Yeah.
Cool. Thank you very much.
Yeah.
Okay. Next is Ruidong with an update on hop-by-hop authentication in CCNX or NDN. Can you do one more? Do you have to?
Hello everyone, I'm Ruidong from.
That's the wrong one.
This is the wrong slides. Yes, I'm Ruidong from NRCD Japan. Today I will present the updates on the hop-OS draft, hop-by-hop authentication in content-centric networking and named data networking. Last time at IETF 105, I presented the basic design of the hop-OS. That time I get some feedback on the motivation and the initial trust establishment. So this time I give some update for the draft. The update in version 01 is that include the motivation clarification and more discretion on the initial trust establishment. First, this is a simple introduction on the content-centric network and named data networking. There is a consumer send out the interest, and then the interest will be forwarded hop by hop. Finally, it reaches the copy holder, and then copy holder replies with data. And in this procedure, the three entities involved. One is publisher, consumer, and a copy holder. We consider two adversary models. One is the content poisoning attack. That is the attacker impersonates the copy holder to provide the fake or corrupted data. Currently the content is only signed with the key of the entity who publishes this data. So the consumer may always retrieve the wrong or fake data because the routers cannot detect the validity of the data. So it is necessary for the other router to use the authentication service to authenticate the data. So the second attack we consider is the intrusive flooding attack. That is, attacker can impersonate the consumer to request the data. There are much existing work focusing on the restricting the intrusive sending rate. So it is we identify that it is necessary for the copy holders to use the authentication service to authenticate the intrusive packet. This is a detailed, some details of the content poisoning attack. The attacker provided the fake or corrupted data. Then the consumer send out the interest. Then the data, fake data, will be replied to the consumer one. So this is a problem one, that the consumer always receives the wrong data because the intermediate router do not detect the validity of the data. So after that, the data was cached hop by hop. This data, after that, the consumer too send out the interest, and then also the wrong packet or wrong data will be replied to the consumer too from the cached memory of the closed router. So the second problem is that the fake data are further cached, which pollutes the routers as a virus spreads. So we identify two requirements here. The first requirement is that all the routers along the path need to verify the data before caching. But we don't like to avoid heavy and complex tasks in the central management system. The second requirement is that the consumer need to verify the copy holder and the data retrieval path to identify the polluted entities besides the data verification. This is introduction of the intrusive flooding attack. That is the consumer send out the flooded interest to the network to malfunction the routers. So the first problem is that the network may be broken. Of course, there are some much existing work on focusing on the rate limiting. So, but finally, there are still some malicious interest can still reach the copy holder. So the copy holder still need to provide some provide the data. So it is not an ideal solution. So we identify two requirements here also. The first one is that the last hop router needs to eliminate the chance of the intrusive flooding attack. The second requirement that is the copy holder need to verify the intrusive packet before replying the data. So the hop-OS, in a summary, that is some summarize advantage of the hop-OS. The hop-OS is a single mechanism enabling the potential authentication from any consumer to the data, to the copy holder, including publisher, and also to the data retrieval path. And it also enables the router to authenticate the interest. So it is a data-oriented mechanism that doesn't necessarily rely on the external servers, but it doesn't exclude the use of the certificate authority, as it is contributed to the suspension chain model we proposed in our hop-OS. But here I'll introduce our modification. And from here, I will give some introduction on the initial trust establishment for the use of the self-certifiable naming. We use the hash of the public key to embed it into the name to prevent the stealing and the spoofing of the existing names. The solution here is use the public key to is embedded into the name to enable it to be certifiable. The name owner can use the corresponding private key to assert its ownership to sign the message sent from this entity with the name. But we need to notice that an attacker can create a new name from an arbitrary public key. However, the attacker cannot impersonate somebody else's name. here is the conclusion. We updated the whole boss draft on the modification, clarification, and initial trust establishment. Thank you.
Thank you, William. Any question? Okay, thanks again.
Okay, thank you.
So just quick laptop change again. So, Kazuhisa-san, can you come up? Yeah, this is adapter hell. I don't think we can do this. Can we use yours? So we had a couple of additional, say, side events on ICN this time. So one was a hackathon activity by NICT and colleagues on the C4 implementation. Another one was a QoS discussion that wasn't really at the hackathon, but that took place on Sunday. So we just briefly like to update you on those. Okay.
So, hello, I'm Kazuhisa Matsuno. So please let me quickly report the C4 project in this hackathon. So, C4 is open source software platform enabling CCN communication, which complied with 2 RFCs. The main objective is to enhance this C4 functionality in the context of the 2 proposed draft. One is CCN info, and the second is network coding for CCN and NDM. So more precisely, in this hackathon, we implemented 2 C4 functions. One is in-network cache control using CCN info, which can enable some operator to check out in-network condition, in-network cache condition, and which data should be cached. And the second is content produce application using which can utilize network coding in the context of CCN communication. So as an achievement, we built and tested the basic plugin module related to these 2 functions, and it's still ongoing. We need to make more flexible and feasible naming scheme and deal with interest packets to improve the performance. So here are these team members. And you can get more C4 information and the source code from this URL. Thank you.
Okay. Great. So that's great to see that people are doing this hackathon activities. So let's do more of this next time. Thank you very much. Thank you. And another laptop switch. Let's see how it goes. Looks better. Yeah, much better.
But I have to get this onto the other screen. Right? There you go. Won't up. Let me switch to mirror.
Okay, no.
Hang on.
Yeah, sorry, the presentation laptop didn't work today. So.
Come on, just to be a
Come on down.
Mandel? I don't think so. All right, we'll just do it from here. So I'm just going to sit down. As you know, we announced a sort of an informal side meeting about what ICNRG might be doing about quality of service stuff going forward. And we didn't get a lot of attendance, but the attendance we got was some pretty good engagement from a variety of people. So I'm just going to quickly run through some of the things we talked about. And our idea is, if people are interested, and I'll take a poll at the end, whether we should have a follow-on informal get-together later this week. We would be targeting the morning open slots for Thursday in order to get together. So we looked at the existing drafts that address various quality of service things, but the discussion ranged somewhat wider. So some of the things people seem to want to talk about is what interesting research can we support by working on quality of service stuff? Do we want to actually try to come up with a defined architecture for doing quality of service in ICN? How much should the experience we have doing quality of service work in the IoT and low-end, low bandwidth, low capability network environment, use that to drive some of our quality of service work, because that's where people have spent a lot of time. Sort of like the high level question is, who cares? If people don't care, there's not going to be enough participation to really make some progress. Some more detailed questions like, do we want to mirror the kind of class-based quality of service capabilities that DiffServ provides, or do we want to also accommodate flow style quality of service capabilities similar to what IMServ does? And who will implement and measure whatever we come up with? Because if we just write specs, that'll be, fun for putting things together, but not really affect things. So we have a whole bunch of notes. I'm not going to go through all the notes. They've been posted to the data tracker. But just to give you a sense of what we talked about, we talked a bit about what the alternatives are for flow classification. We talked about some of our terminology is kind of loose, and we need to clean it up some more. For example, there's already some confusion about why some people think flow and congestion control are sort of very closely related to one another, and other people think those are sort of separate topics, and you want to talk about flow control and congestion control separately, and whether QoS treatments should be bound together with flow classification or not. So there is some sort of general talk about this quality of service architecture polemic that I published a few months ago, and what we should do about that. We're interested in more feedback on that. I think our default, after talking to Colin, is to actually move it through ICNRG, but treat it as an individual submission so it doesn't bias our future work in coming up with a quality of service architecture. I'm trying to think if there's anything in here that you just couldn't figure out by looking at the materials. No, I think that's about it. So please look at this stuff, ask questions, and let me just get a show of hands. Who might be interested in showing up Thursday morning for further discussions on this topic? All right.
That's a number.
So we'll do instead of doing a doodle poll, since there aren't very many options other than really Thursday morning, we'll try and get a room. Yes. It would be in the open slot time from 8 to 9:30, right? So since there seems to be enough interest, we'll go and try and schedule a room and send the room information to the ICNRG list for Thursday morning. Okay.
Okay, great.
I think we're done.
Yeah, so thank you all. So as you have seen, I mean, this was a pretty packed agenda. So thank you all for your contribution and your discipline. So next time we'll have to find a way how to deal with that. So we are likely going for another full day interim. On the other hand, we would also like to encourage more hackathon work. And so this would kind of conflict with the weekend before. So maybe let's discuss this a little bit. So if you want to do some hackathon activities at the next IETF, it would be good to let people know in advance. So that we can coordinate a little bit and make sure that you have good attendance at your hackathon table.
Blue sheets, blue sheets, blue sheets.
Please give us back the blue sheets and
If anybody didn't sign,
enjoy your lunch.
Stand by the door and not let you out. No, I'm not. But please sign if you haven't.
Okay, we are done. Thank you very much.
Blue sheets? Come on, guys. Who has the blue sheets?
Screw up the laptop.
That's okay. I'll forget it.
We didn't try rebooting it.